Yeah. So what was the last topic we saw? Self-inductance. So we can go with the next part, right? That is mutual inductance. Guys, those who are online, are you able to hear me?
Yes, sir.
Yes, sir.
Okay. Yeah. So we saw what is inductance, right? So yes, we saw. Yeah, the lights not on. Wait till no problem. The light is not. It's the switch is there. Next one. Right. So next we will discuss about mutual inductance. Okay. Shall we get started? So the name suggests, right? What does mutual inductance mean? What does it mean? So yesterday, if you saw the concept of self-inductance, what did it speak about? There was one inductor. So that inductor can either be, it can be any closed coil. It need not be a solenoid. See, for the sake of understanding, there is a basic symbol for an inductor, but that doesn't mean the inductor is always a solenoid. Inductor can be some coil. So yeah, having said this, when I talk about self-inductance, right? When I talk about self-inductance, current is passed through the coil. Are you guys able to see me? The online people are able to see me?
Yes, sir.
If I have to show any demo. Okay. So current was passing through the same coil, and flux was linked with the same coil. Flux was changing through the same coil. So everything happened within the same coil. That is why we use the word called as self-inductance. Whereas if there is current passed through one coil, and if there is a change in flux taking place in the neighboring coil, I repeat, if there is a current passed in the first coil and change in flux is taking place in the second coil, then what will happen in the second coil? If there is a change in flux taking place with respect to time in a coil, what will happen? EMF is induced over there. So current is passed through one coil in Sonata. The coil through which current is passed is generally called as primary coil. And the coil through which the EMF is generated is called as the secondary coil. It's called as the secondary coil. Is that clear? Is it clear? So let's say this is one coil. This is another coil. Okay. I'll just give you some scenarios. Okay. This is scenario number 1. And this is number 2. Okay. So in scenario number 1, let's say the current is passed through the first coil. Let's call it as I. And this I will generate a magnetic field. Right? it will generate a magnetic field, and that magnetic field is getting linked to the second coil. So initially when the current through the first coil was 0, then the magnetic flux linked with the second coil would have also been obviously a 0. When you switch it on, the current would have increased from 0 to a steady state value. During that process, what would have happened? There would have been a slight increase in the value of flux that is getting associated with the second coil. So in this process, can I say that an EMF is induced in it? Right? Can I say that there is an EMF induced in it? Accepted? No. In a similar way, if I have the current passing through the first coil, then there is a magnetic field which will be into the plane. Accepted? Then there is a magnetic field which is into the plane, and this magnetic field will create a flux in the second coil also, due to which there is an EMF induced in the second coil. Correct? So out of these two scenarios, in both the scenarios, what is happening? There is one coil where the current is passed and second coil where the EMF is induced. In out of these two processes, which one will create more EMF? Scenario 1 or scenario 2? Why? Yes. Scenario 2 will create more amount of EMF, or I can say more amount of flux is associated with the second coil. In second scenario, because of the fact that they both are placed coaxial to each other. Or I can, to be more specific, I can say they are concentric. Whereas the first case, they are not concentric, rather they are coaxial. What do you mean by coaxial? They share the same axis, whereas concentric means they share the same center. So which one is more efficient? The second one. Is it clear? So whenever you want to generate more amount of inductance, you want to create more effect of inductance in the second coil with the help of first coil, you always try to place them in such a way that their centers are coincident. Okay, this is about one circle. What will happen if you have a solenoid? That we'll see next. Okay, so first make a note of this.
Sir, can you scroll up?
EMF is connected. That is due to the external. But we generally ignore the value of self-inductance. But in reality, it will happen. It will be lesser, not a big more. Right. So the coil where the current is passed means you have connected it to a potential source is called as, where did you hear it? I told her. It's called primary, and the one where the EMF is induced is called as secondary coil. So just to differentiate it. Okay. So based on this, I want to ask you some scenarios. Let's say there are two coils like this, 1 and 2. Wherever I write 1, it is primary. Wherever I write 2, it is secondary. That is the understanding for us. Okay. And I have a scenario where this is 1 and this is 2. Okay, this is case 1. This is case 2. Okay. Case 3. Which one is more effective? Case 3 is the most effective, followed by case 1, followed by case 2. Because in case 1, what can happen? This field will get linked here. Because here I have literally drawn a solenoid. Okay. So what will happen? In case 1, the magnetic field from the first coil is generally getting linked to the second coil because along the axis you have magnetic field. Whereas in the case number 2, in the perpendicular direction you do not have magnetic field. Clear? So that's what happens. So 3 is greater than 1 is greater than 2. So done, I'll proceed with the next step. Can I? Yeah. Okay. Now see, current is passed through the first coil. Okay. So if I say current is passed through the first coil, I'll call it as I1. And flux is associated with the second coil. Okay. Can I say the flux that is associated with the second coil is N252? So the flux associated with the second coil is directly proportional to the current passing through the first coil, unlike yesterday's scenario. If you once revisit the concept of self-inductance, there what did I write? The flux associated with the coil is directly proportional to its own current. Is that not the case? Right. Whereas in this scenario, what is happening? The flux associated with the second coil is proportional to the current that is passed through the first coil. Okay. So N252, I can write it as M21 times I1, where M stands for mutual inductance. But when you write mutual, you need to write the relative values. What do you mean by relative? You need to write a subscript of which number with respect to which number. So how do you read it? Mutual inductance of 2 with respect to 1. So mutual inductance of 2 with respect to 1 is this value. So M21 is equal to N252 divided by I1. So what is going to be the SI unit for it? What is going to be the SI unit for it? It's the same thing again. As that of self-inductance, it is Henry. Okay. Now, if I swap the values in the sense If I make the second coil as the primary coil, so in this scenario, I'm writing it as 2, for example. I am passing the current through the secondary coil and EMF is induced in the first coil. Then what can I say? So flux associated with the first coil is directly proportional to the current through the second coil. So N151 will be equal to how much? M12 I2. So M12 will be equal to N151 divided by I2. So it's very simple to remember. If it is M21, right? What is the first number? 2. So 2 will be in the numerator, 1 will be in the denominator. அதே மாதிரி M12 na 1 will be in the numerator, 2 in the denominator. Generally in the numerator, whether it is self-inductance or mutual inductance, in the numerator you write flux, in the denominator you write current. So recollect the formula yesterday, we did a derivation also. L is equal to N5 by I and we did a derivation. So same logic here. Is it clear? Right. Shall I proceed? Now, having said this, we need to derive the formula for, or I'll take a scenario like this. If somebody is copying, please do it. Okay. Now, having this in mind, let's try to derive the mutual inductance of two long coaxial solenoids. This is an important derivation again. So write down the heading as mutual inductance of two, underline the word long. Mutual inductance of two long coaxial solenoids of same length L. They have the same length L. Okay. So if you try to understand the scenario, right, look at the diagram. There are two solenoids, S1 and S2. See, generally if they use coils, right, they will write it as C1 and C2. If they use solenoid, they write it as S1 and S2. So solenoid 1 has a small radius R1 and solenoid 2 has a radius of R2. But they mentioned it to be long solenoid. Why did they mention long solenoid? Because we know the formula for a long solenoid. What is it? B is equal to mu naught small n into I. So B is equal to mu naught into small n into I. And they both are of same length. Let's say the number of turns that solenoid 1 has is N1. And the number of turns that solenoid 2 has is N2. Okay. Now our job is to find M21 and M12 and the relation between them. Okay. So first, we will start with M21. Okay, I'll start with M12 because M12 is comparatively easier. So M12 is how much? N2, N151 by I2. So N151 tells me that I need to find the total flux associated with the first coil. Okay. So N1 is N1 only. How can I write the flux as? Flux is B A cos theta. You divide the whole thing with I2. Accepted? Now the question is, who's producing the magnetic field? Where is the current pass? Current is passed through second coil. So second coil is the one that generates the magnetic field. So though we wrote it as phi1, you should write it as B2. Okay. Then what is the area of the coil that is getting associated with this flux? What is the area of the coil? So B2 is everywhere, but I'm concerned about the flux through the first coil. So I will take only this area into consideration. I wind it again. So I'll only take this area into consideration. Can I do that? N1 into, what is the value of B2, guys? Mu naught small n2 into I2 multiplied with area of first coil, that is pi r1 square into, what is the angle between magnetic field and aerial vector? Magnetic field and aerial vector in this scenario is again same direction, so cos 0, the whole divided by I2. Can I write it like this? When that is a case, I2 and I2 will get cancelled. So what am I left out with? So you are left out with mu naught n1 into small n2. How can I write it in terms of capital N? Capital N2 divided by L into pi r1 square, and this is going to be the value of m1. Is that clear? So actually, if you see the derivation, it is only 3 steps, but you need to be careful with B and A values. Purida, write it down. Those who are online, could you understand?
Yes, sir.
Yes, sir.
Okay. Good.
Yes, sir.
If I write it as 1, 2, ரெண்டாவது நம்பர் தான் கரெக்ட். ஸோ டினாமினேட்டர்ல என்ன இருக்கு? I2 தான் செகண்ட் காயில்ல கரெக்ட் பாஸ் ஆகும். First. That is why we write it as M12. Because flux is generated, so you need to write the magnetic field, right? Flux. So what is flux? Magnetic field multiplied to the area into cos of the angle. Magnetic field who can generate? Only current carrying conductor can generate. Who's the current carrying conductor? Who? Another B2. Right. Now can we try to find M21? So for M21, what is the formula? N252 divided by I1. Is it right? Let me take the same diagram. And paste it on the right hand side. Okay. N2 is how much? N2 only. What about phi 2? B A cos theta divided by I1. Right? Now see. Magnetic field is generated due to the first coil, B1. Flux is associated with the second coil. Is it right? So it will be A2. Am I right? Wrong. Because when you talk about a long solenoid, for a long solenoid, where is the magnetic field present? Magnetic field is present only within itself for a long solenoid. When it is present only within itself, then the maximum area to which magnetic field is confined to is the area of the first coil itself. This is point clear. This is the only tricky part. Because if you feel it is exactly the reverse of previous step, it is not. So in both the scenarios, what are you supposed to write? You should write only area of the smaller coil. Is that clear? Right? So here what will happen is it will be B1 into A1. I marked it with red C. B1 into A1 into cos theta divided by I1. Right? Now comes the next step. N2 into what is the value of B1? Mu naught.
B1, sir.
Because for a long solenoid, where is the magnetic field confined to? Only inside it. No. When will you take area 2 into consideration? When magnetic field is present here also. But here, there is no magnetic field at all. Nitish, are you able to understand?
Yes, sir.
Yes. So mu naught into N1 into I1 into area of the first coil is pi R1 square into cos of how much? You're not well, huh? You're fine. Cos 0 degrees divided by I1. So I1 and I1 will get cancelled. So what are you going to have? Mu naught N1 into capital N2 into pi R1 square. So can I write this as mu naught N1 into capital N2? I can write it as N2 divided by, sorry, my mistake, wait. N1 I can write it as, small n1 I can write it as N1 divided by L, and here you have N2 into pi R1 square. So what are you left out with? Mu naught N1 N2 pi R1 square divided by L, which I'll call it as M 1 2, no? Or 2 1, no? So it is called as M21. So what do you understand from this? So M21 and M12 have the same value provided they both are of same length. Had they been of different length, then the denominators L1 and L2 would have been different. Okay, so please make a note here. So both the solenoids have this, M12 and M21 are the same, provided both the solenoids are of the same length L. Am I clear? Yeah. Okay.
Sir, can you show the M12 for a minute? Yes, sir.
This is M21. This is all about the mutual inductance of two solenoids, and this derivation is important. Mark it as important. So for self-inductance also, I derived the value and showed it to you. And yesterday I explained you what is the significance of an inductor also. What is the significance of an inductor? It will oppose, yes, it will oppose the rate of change of current taking place. Okay. The next heading would be energy stored in an inductor. Energy stored in an inductor of, okay, I'll add this word, of self-inductance capital L. Okay. So let's say there is an inductor of length L. Sorry. There is an inductor of inductance L through which current is passing. Okay. Now I want you to revisit and tell me what is the relation between EMF and inductance. Like relation. So L is equal to E divided by di by dt in a magnitude. Because generally, if you write it without magnitude, E is equal to minus L into di by dt. I hope you understood why is it so. Because you know that n pi is equal to Li. When I differentiate it, I'll get EMF as minus E. So minus E will be equal to L into di by dt. But here what is happening? L will be equal to magnitude of EMF into di by dt. So EMF is equal to L into di by dt. Can I write it like this? Now what I'll do is multiply with I on both sides. When you multiply with I on both the sides, you get EI is equal to L into I into di divided by dt. Okay. But what is E into I called as? The product of voltage and current is called as electrical power. Correct? So can I write this as P is equal to L into I into di divided by dt? But what is the basic definition of power? What is the basic definition of power? It is work done per. So dw by dt will be equal to L into I into di divided by dt. So dt and dt are lost. You get dw will be equal to L into I into di. Accepted? So since we are trying to find the energy, if you are able to calculate the amount of work that is done, that will give you the energy. So when I integrate on both the sides, I get W is equal to integral of L into I into dI between 0 to I. Okay. So W will be equal to L will come out. Integral of IDI is I square by 2. And when you apply the limits of 0 to L, 0 to I, you get it as half L I square. That's it. Sure. From here, Right. So it is half Li square, and this is the energy that is stored in an inductor, and this energy will get stored in the form of magnetic field. Do you remember there is a formula which is similar to this? You wrote this also last week.
Half CV square.
Energy stored in a capacitor is half CV square. So half CV square. Instead of capacitance, you have inductance. Instead of potential difference, you have current. Is that clear? So in the form of magnet, so energy is stored in the form of magnetic field. Okay. Now based on this, there is a problem. So the problem is obtain the expression for, so read the question, obtain the expression for the magnetic energy stored in a solenoid in terms of magnetic field B, area A, and length L of the solenoid. Okay. So they are asking you to derive the value of magnetic field. So energy stored in the form of magnetic field. Energy is represented by the symbol U. B stands for magnetic field. So UB is equal to half into Li square. Okay. You want the magnetic field, the energy stored in the form of magnetic field, to be derived in terms of capital V. Okay. So half Li square is there. Let this be equation number 1. Now, what kind of a device is it? It's a solenoid. For a solenoid, what is the value of B? B is equal to mu naught into N into I, which implies I is equal to B divided by okay. Take this and substitute it here. So UB will be equal to half into L into I square is B naught square divided by mu naught square into L square. Is the point clear? But UB is also equal to, how do you write L in terms of mu naught small n A and L? So yesterday we derived a formula for self-inductance of a solenoid. What is it? I told you are expected to remember that. Mu naught small n square A into L. So half into mu naught small n square A into L into B square divided by mu naught square n square. So n square and n square will get cancelled. This will be equal to half into 1 mu naught is also gone. Half into B square into AL divided by mu naught. This is the value of UB. Okay. So if you're done with this, the second part is how does the magnetic energy compare with the electrostatic energy stored in the capacitor? So magnetic energy is stored in the form of obviously magnetic field. And for a capacitor, it is direct. Okay, they gave it in terms of okay. So for that, actually, there is a small mistake here. How does this magnetic energy different from energy density? Okay. So for that, what we need to do is I am asked to derive the energy density stored in an inductor. So what is the energy density? Can I rub this part? Now I'm going to calculate energy density stored in it. What is the energy density? Energy by unit volume. So we just now derived the energy in terms of B square. What is it? B square A into L divided by 2 times mu naught, the whole divided by what is going to be the volume of the inductor. If I take an inductor to be in this form, this is the cross-sectional area multiplied with the length. Just A into L. So AL and AL are gone. I get half into B square divided by mu naught. This is the energy density stored in an inductor, and this expression is important for each chapter. In each chapter is electromagnetic waves, right? There we'll be discussing about the energy density of electric field and magnetic field. So yeah, so B square divided by 2 mu naught is going to be the energy stored in the inductor. Energy density per unit, energy density in inductor. Yeah, tell me that.
Sir, here they are asking magnetic energy only, right?
Actually, that is a mistake. Actually, it is not energy. It should have been magnetic energy density.
Okay.
Okay. So when you talk about energy density, now what can you say? Energy density in an inductor is directly proportional to magnetic field square. Energy density in inductor is directly proportional to square of the magnetic field and inversely proportional to the permeability. Whereas the energy density in an inductor, in a capacitor is how much? Half epsilon naught E square. You remember this? You have seen this expression. So half epsilon naught E square. What is the value of epsilon? Okay. Here I can say that the energy density is directly proportional to permittivity and directly proportional to the square of the electric field. That's what they've given it in this statement. You can read it. You're able to understand? Am I clear or not? Any doubt? I'm saying energy density in a capacitor is directly proportional to permittivity and it is proportional to the square of the electric field. But energy density in inductor is inversely proportional to the magnetic, inversely proportional to the permeability and directly proportional to the field square. Okay. So if at all you have a doubt of how did we get that half epsilon naught E square, it is very simple. You know half CV square divided by volume is going to be energy density. So half into energy stored in a parallel plate capacitor is how much? Epsilon naught A divided by D into B is how much? B is E divided by D because it's E into D because electric field is negative of potential gradient. So E into D square divided by volume is A into D. Okay. This D and the denominator D will get multiplied. Both these D's will cancel this D square. Okay. And A will cancel this A. So what are you left out with? So this is how you got. Okay. This we have already discussed in the second chapter. If at all you have forgotten, please write it. So there are
Sir,
two
can
more.
you scroll up a bit, sir?
Sure. Is this fine?
Yes, sir.
Okay.
Yes, sir. Thank you, sir.
Okay. Listen. Now, there are two more topics that are left out. One is AC generator, and the second is called eddy currents. Okay. So first, we will see what an AC generator has to tell us. But before that, I'll show you a small video. So I hope you're able to see it, right? Now you see, the topic is about AC generator. So name itself is suggesting AC means alternating current, and generator is the one which generates basically EMF. Okay. So throughout the chapter, we have been seeing only one thing. If there is a change in magnetic flux taking place with respect to time, then you can say that there is a EMF induced. Now let's think of the logic even before we get into the concept, right? Let's think of one logic. What should a generator comprise of? So you need a source of magnetic field, and the magnetic field that is getting generated should be linked with the coil. So are these two not the logic? Only when the magnetic field is linked with the coil, you can talk about flux. And what are you supposed to do to that flux? Change it. Okay. So from the beginning, we have been discussing flux is dependent on three parameters. What are they? Magnetic field, area, and orientation. Right. So here, what we will try to do is we'll keep the magnetic field constant. For that, I need to use permanent magnets in such a way that they have concave shape. Right. So concave shape magnets can generate uniform magnetic field, into which I will place a coil which is of a constant area. So what did I do? D is kept constant, A is kept constant. So what is that we need to change? We'll change the orientation. So using all this logic, we can conclude that if you are able to design a device which works on the principle of converting mechanical energy into electrical energy. I repeat it. If there is a device which is able to convert mechanical energy, which is able to take the mechanical energy into consideration and give us electrical energy, then one of such devices is generator. I'm not sure if there are any other devices, that is why I use one of such devices. So this is generator. So having said this, look at it. So I'll be going a little fast because they would have explained Faraday's law.
In the form of an alternating.
So you're able to observe you have a concave shaped magnet. you have a concave shaped magnet which is of north pole and the south pole, into which you place an armature. You place a coil. Any idea about what is the name of the coil? It's called armature coil. You would have heard of this word. In your 10th. That is a DC generator with AC generator. So to this armature coil, you are connecting two rings, metallic rings, which are called as slip rings. Okay. In the outer part, you have connected two knobs kind of thing. You are able to see two rectangles. Any idea what those rectangles are? The carbon brushes. So they act as the electrical connectivity between the slip ring and the source where the EMF is to be generated. Okay. So galvanometer is basically used to observe the direction of current. Okay. So I want to stress on one important point here. Galvanometer cannot detect AC. It will not detect AC. But in this case, what we are doing is it is only used as a testing piece to understand that what is the direction in which the current is getting generated. Okay. Now what will happen is the magnets are like this. So there is a magnetic field existing. Okay. Let's say the magnetic field is like this, in this direction. Now if you place a coil in this way and the magnetic field is in this direction, what would be the flux associated with it? Magnetic field is in this direction. Coil is in this direction. So what would be the flux associated with it? It is zero because B is in this direction, A is in this direction. They both are perpendicular to each other. They get cancelled. Whereas from zero magnetic flux, if I am able to make this armature coil rotate and I bring it to this position from 0 to 90, is there a possibility for me to change the flux? Am I increasing it or decreasing it? You are increasing it. So when it comes to this position, can I say it has maximum value? Again, from here, when it rotates, it takes 180-degree turns. Here again it is 0. So from maximum it has got decreased to 0. Again it will take a turn, that is 270. When it comes to 270, again the flux is going to be maximum, but in the opposite direction. Why I use the word opposite direction is because if you take one side to be the area, you should always take the angles only with the side which you considered as area for the first step. You should not keep changing the direction of area whenever it is taking a turn. So initially when the area is like this, from here, when it goes in this direction, magnetic field is also in the same direction. Then the flux becomes maximum. Again, when it is taking a turn, the magnetic field is still like this, but the aerial vector will be in this way. Again, flux is 0. Now, the aerial vector will become like this. Magnetic field and aerial vector, they both are in opposite direction. So what happens to the flux? So flux is changing from 0 to maximum, maximum to 0, again 0 to maximum, maximum to 0. So by this kind of a change happening, but when it is going to maximum for the second time, it is going in the reverse direction. It is going with the negative value. So it is negative in the, it is maximum in the negative direction. Why? Because the orientation between the coil and the magnetic field is 180 degrees. So having said this, if at all you try to derive a mathematical expression of how the EMF associated with the coil is going to be with respect to the angular frequency, okay, then we will be able to get an expression. Shall we try that? So you're able to understand this diagram? You have a permanent, so this is the kind of diagrams you're expected to draw. So you have a north pole and a south pole into which there is a coil placed, and the coil has an axis associated with it, which we call it as axle. Then it is connected to two slip rings, and across the slip ring there are carbon brushes that are connected from which the alternating EMF is generated. Okay, that is the simplest diagram possible. Now, initially, what can I say the flux is? Okay, I'll go with this expression. So we know that flux is equal to B into A into cos theta. So B is generated due to the permanent magnets. Accepted? So magnetic field is generated due to the permanent magnets. Area here is related to the armature coil. Okay. Then what about theta? Theta is omega into T. Because I need the variation of flux as a function of time. So flux is equal to BA cos theta. This is equal to B into A into. In the place of theta, I write it as omega into T, where omega is the angular frequency with which the armature coil is revolving. Did you understand how I got this omega T? Because S is equal to UT plus half AT square. Similarly, theta will be equal to omega T plus half alpha T square, where alpha is the angular acceleration. When the coil is revolving with a constant angular velocity, alpha is 0. When I put this as 0, theta will be equal to omega into T. So flux will be equal to BA cos omega T. So when you differentiate this further, I can be more specific. See, when I talk about an armature coil, it is not going to have only one turn. It will have n turns. So when it has n turns, you can put n here. Purida. Am I clear, guys? So if I give you the flux as a function of time, then is it not possible for you to derive EMF? Can you derive the EMF of it? How do you do that? So d phi by dt will be equal to, okay, just give me a minute, I'll write it in a fresh page. So first step is phi is equal to BA cos theta, and phi will be equal to BA cos of omega t. Then what about d phi by dt? Okay, I'll add an n here. You're able to understand why I added the n. Flux will related to one turn is BA cos theta, related to n turns will be NBA cos theta. So this will be equal to n into B into A into cos omega t. I can write it as minus sin omega t into omega. Chain rule. So this will be minus NBA omega into sin omega t is d phi by dt. The minus sign can come this side. So minus d phi by dt will be equal to NBA omega sin omega t. This minus d phi by dt is what is called as EMF according to Faraday's law. And this will be equal to this NBA omega is called as E naught into sine of omega t. So E will be equal to E naught into sine of omega t, where this E is called as C, instantaneous EMF, and E naught is called as the peak value of EMF, and sine omega t is the function according to which the EMF is changing. Is it clear? See, this particular expression is a connecting point for the next chapter, and the next chapter's name is alternating current. So if I need to know what an alternating current is, first I need to know what an alternating voltage is. Mathematical equation, and there is the equation. I hope it is clear. Is that right? Now comes another important point. How is the graph going to look like? This is not the graph for sine. So this I can write it as E naught sine omega t, where this is the instantaneous EMF and this is the time. If I drop a perpendicular, this will be E naught, and this will also be E naught. So that is what we mean by the maximum value. Am I clear with this? Yes. So that's how it works. Please make a note of all these points. Sorry? Is this fine? See, that NBA omega, I want you all to remember. It is used in problems also. Is it clear? So one last topic, that is eddy current. We'll see it in the next class. That the chapter is over. And remember this expression, alternating current, this is the one which will start all the derivations. So this is the equation with which all the derivations are started. Clear? So revise it. And yeah, that's it from my side. So those who are online, any doubt, guys?
Yes, sir.
Okay.
No, sir.
Okay. We'll wind up then. Yeah, tell me.
Sir, I couldn't attend the test on last Saturday, so can I do the test as a home assignment tomorrow and submit it?
You can do it as assignment because the corrections are already over. Marks will get uploaded today.
Okay, sir.
You do it as assignment and upload it.
Okay, sir. Thank you, sir.